Welcome to VirtualLab Fusion, the digital twin platform for light. This isn't just software, it's a new paradigm, one designed to accelerate your R&D and let you innovate without boundaries. Let's start with a challenge every optical engineer faces. Modern optical systems are built from many pieces: lasers, lenses, fibers, diffusers, metasurfaces, gratings, samples, detectors. And for each piece, there's often a specialized simulation tool, highly accurate, finely tuned for its specific task. But here's the catch. These tools were never designed to work together. They don't speak the same language. They don't share data seamlessly. They weren't built for system-level modeling. So the real question becomes, how do you simulate an entire optical system when the tools for the pieces simply aren't made to connect in a user-friendly, interoperable way? Imagine a different kind of laboratory, a virtual lab, where every real-world source, component, and detector is replaced by its optical digital twin. Each twin is an intelligent, functional replica. It mimics the exact optical behavior of its real-world counterpart. In this lab, you stop worrying about software compatibility, data conversion, or manual interfaces. Instead, you start focusing on what truly matters: building the system, investigating its performance, optimizing the design, and generating innovative solutions faster than ever before. So, what does it take to turn this vision into reality? What are the key requirements to build a truly interoperable digital twin platform for light? The first requirement is perhaps the most fundamental. We need intelligent, self-modeling twins. We must move beyond the old idea of a single, one-size-fits-all simulator. Instead, each digital twin must have its own tailored, inbuilt simulation model, optimized for its specific function. But we go even further. For critical components, we offer different versions of the same twin, each tuned for a different balance of speed and accuracy. Need rapid iteration? No problem. Choose a twin with a faster approximated model. Final validation. Easy. Switch to a high-accuracy version. This flexibility puts you in control of your simulation workflow. But this requirement creates a challenge. In classical simulation, the model and the mathematical representation of light are locked together. A simplified model means simplified light data, rays, scalar fields, or vector fields. This legacy link means twins built with different models can't fully communicate. They become isolated islands of simulation, and that breaks the very interoperability we're trying to achieve. Now, you might think, why not just use the most rigorous model for everything? The answer is practicality. Simulating every component with full electromagnetic rigor would be impossibly slow. The goal isn't to eliminate approximations, it's to make them work together. We need speed, but we also need accuracy. We need a way for simplified models and rigorous models to coexist and communicate. This leads us to our core innovation, the field-centered approach. We set two non-negotiable requirements. First, all twins must use electromagnetic fields as their fundamental communication language. Second, we completely unlink the level of approximation from the light representation itself. The result? Electromagnetic fields become the universal lingua franca, a common data format that all twins understand for their inputs and outputs. Full interoperability is not just a goal, it's built into the foundation through this shared communication protocol. With our field-centered approach, every twin communicates using the same fundamental language, electromagnetic fields. Whether a twin employs a fast approximate model or a rigorous simulation without approximations, it consistently inputs and outputs electromagnetic field data. This field-native communication protocol guarantees seamless interoperability across the entire optical system, independent of each twin's internal modeling complexity. But how is this even possible? It requires a fundamental reformulation of classical approximations. We realized that most common approximations, even geometrical optics, can be expressed directly in terms of electromagnetic fields. We follow the insight of Born and Wolf. We treat geometrical optics not for rays, but as laws that govern the propagation of electromagnetic fields. This means the approximation lives in the propagation model, not in the light representation. Now, if you still need ray-based data for analysis or export, that's fully accessible. Rays are derived from the fields when needed, not used as a replacement. This preserves both flexibility and fidelity. You might wonder, does working with fields mean slower simulation? Not at all. Speed is determined by the model choice, not the field representation itself. The key insight: we intelligently select from a spectrum of approximations, using fast models like geometrical propagation where diffraction effects are negligible, while applying other approximations or rigorous methods where needed. This flexibility allows us to find the optimal accuracy-speed balance for each twin and propagation path, enabling near-instant evaluation where fast approximations are justified while never being locked into system-wide modeling constraints. You get full interoperability without sacrificing performance. To bring all of this together, you need a conductor. That's the field tracing engine. It orchestrates the light propagation between all twins, managing the electromagnetic field data without interfering with their internal models. It's the invisible backbone that makes the platform work seamlessly. So, let's recap the blueprint we've built. Autonomous digital twins, each an intelligent agent with encapsulated simulation intelligence. A universal field-native communication protocol using electromagnetic fields. A foundational principle that decouples approximation level from field representation. And a scalable orchestrator in the field tracing engine. The result is a truly interoperable digital twin platform for light. This isn't just conceptual architecture, it's engineering reality being delivered. After years of foundational research and development, we're launching VirtualLab Fusion 2026.1, our first major release built entirely around this digital twin philosophy, representing a quantum leap toward the complete digital twin platform for light. One of the most exciting features is instant access and integration. We're launching the VirtualLab Fusion Optical Digital Twin Hub, a public online central access point for all digital twins, fully integrated into VirtualLab Fusion. Browse, select, and click to add twins directly into your system. No manual downloads, no compatibility headaches. The hub provides organized discovery and direct workflow integration from a single interface. But how do you choose the right twin? Each twin in the Digital Twin Hub comes with a detailed specification sheet that documents its model, inputs, outputs, and its speed versus accuracy profile. You can compare versions and select the perfect twin for your task, fully informed, all within the streamlined hub interface. Now, let's talk about how you build your system. If all the twins you need are already in our hub, great. You can start building right away, and your simulation will just work. But what if a twin you need isn't yet available? You have two clear paths. First, you can request it directly from LightTrans. Let us know what you're missing, and we'll provide you with roadmap information on when that twin can be expected. Second, and this is especially powerful for experts, you can build it yourself using our Twin SDK. This is our software development kit, which is under active development. It empowers you to create proprietary digital twins, protect your intellectual property, and integrate them seamlessly into the platform. So whether the twin exists today or not, you are never blocked. You can move forward with us or on your own terms. The foundation is built. The future lies in the twins, shaped by your challenges, guided by your priorities, and built together as we develop the optical design solutions the market needs most. So, let's build the future of optical design together.